Okay, this will be our third lecture on Z-transforms, all part of Chapter 5. Today we're going to make a brief introduction, our discussion of the unilateral Z-transform, and we'll spend most of our time talking about Z-transform properties. Those properties are mostly the same between unilateral and bilateral transforms, but there are some slight differences, so we do need to know the basics of a unilateral Z-transform. From our previous lectures, we had talked about the bilateral Z-transform. So if I have a signal x of n and I want its bilateral Z-transform x of z, I know that that is a summation on n going from minus infinity to infinity of the signal x of n weighted or multiplied by z to the minus n. That's the bilateral Z-transform, right? So we got the bilateral Z-transform. And we know that in order to make that complete, if we want to have a complete representation of the bilateral Z-transform, we must include a region of convergence. That region of convergence provides the information so we know whether signals are, for example, left-sided or right-sided. If we want to think about the unilateral transform, just like the unilateral Laplace transform, the only difference from the bilateral is that it's going to change that lower limit from minus infinity to 0. So the unilateral Z-transform has the assumption that signals are causal, and it reflects that in the sum limits going from 0 to infinity. So we can write that out that the unilateral Z-transform assumes causal signals, right? Causal signals. As a result, when we write this guy out, I might write this out as XU. Just remind us that it's a unilateral transform. This is going to be a summation. It's going to go on n, but now we're just going from 0 to infinity instead of minus infinity to infinity. We still have our signal x of n in there. We still have z to the minus n. The thing I would notice on this unilateral, so this is the unilateral Z-transform, right? Unilateral Z-transform. The thing I would note on that is that we don't have to. So we don't have to specify the region of convergence because the Z-transform unilateral assumes causal signals. Because of that assumption, that underlying assumption of the Z-transform in the unilateral case being causal signals, you wouldn't have a left-sided signal in it. They would only be right-sided. And from that, we can infer a region of convergence. Standard practice then is to go ahead and compute out the unilateral transform. And even though a region of convergence does exist, even though a region of convergence can be specified and doesn't hurt to specify it, many people do not specify it just because you can infer it from the fact that we're dealing with the unilateral transform. I'll leave it up to you, but I would make the comment that if you do a bilateral transform and you don't specify the region of convergence, it's definitely wrong. If you do a unilateral Z-transform and you specify a region of convergence, there's no harm in that. You can do that just fine. You can also infer it if it's not specified. Okay, so we got the basics of a unilateral transform, and what we'd like to do now is transition over to where we can talk about these Z-transform properties. So let's go ahead and think about properties of the Z-transform. So I'll write that out. We're looking at Z-transform properties. If you remember when we talked about the Laplace transform, we talked about a bunch of properties of that transformation as well. Many of the same type of properties are also going to be present here for the Z transform, and they serve the same kind of purposes. So we'll try to make our way through this in a way that we can understand them, but also not spend too much time going over stuff that we've already seen before. To start us out in this particular case, I'm going to go ahead and begin with some knowns. I'm going to just assume that if I have a discrete time signal x of n and go ahead and let it have a transform x of z, and if it was a bilateral case, could be either, but if it was bilateral, we'll just assume it has some region of convergence. We'll call that r sub x. We can also have another signal. We'll call that y of n, and we're going to go ahead and let it have a transform y of z. Again, it could have some region of convergence r of y. And what I'm going to do is I'm going to just use that information as we develop some of these properties. The first property we'll talk about is one that we really should expect for a Laplace transform, a Z transform, any of these guys. Laplace and Z transforms both are linear operators, and so it's no surprise that we have a linearity property as well. The linearity property is really just that idea of superposition, that superposition does apply even to this transform domain. So if I look at the linearity property here, it looks something like this, that if I take some scale factor A times a signal x of n, and I add to it a scale factor B times some other signal, call it y of n, and I'm interested in the Z transform of that linear combination, the linearity of the Z transform guarantees that what comes out is the same linear combination, just now of the transform signal. So ax of z plus by of z. Now, if this is a bilateral transform, we also need to specify a region of convergence. We know that x of z converges for some rx, y of z converges for some ry. For the combination to converge, we have to satisfy both convergence credentials or criteria, and so we're going to need the intersection of those. So in general, we think of the region of convergence of that linear combination of x and y as being the intersection of their individual regions of convergence. There is a little additional detail on this. I'm going to say that the region of convergence of this sum is at least, it is at least the intersection of Rx and Ry. We will want to spend a little time trying to figure out why there would be this extra bit of language in there, the at least. I think it's reasonably obvious in this particular case why we have to satisfy both Rx and Ry. If we satisfied Rx but did not satisfy Ry, this other piece here, byz, would blow up to infinity, and that would kill this other stuff. It would all not converge. Same sort of thing if it went the other way. We need both of those guys satisfied. So what's the at least about? We can do this at least, or at least get an understanding about the at least if I do a little example. So I'm going to go ahead and pick an example of a couple of signals, x and y, and I'm going to do a combination of them, and I'm going to take a look at what happens to that combination under transformation. And I'm picking a particular case where I can demonstrate this condition of at least. So let's go ahead and pick a pretty simple x of n. I'm going to let that x of n be u of n, just a causal DC signal. So we've looked at this one before. We know what its Z transform is. This has a root, if you will, at 1. It's like a 1 to the n u of n. And we're going to get a transform Z by Z minus 1. If we were doing this in a bilateral sense, which makes sense here, it's how I'd like to do it anyway, we know that we have to have a norm of Z being greater than where that root is. So at 1, or at least the size of 1. So norm Z greater than 1 is the region of convergence. And we could call that whole thing, right? That's that Rx if you want to talk about the notation we used above. I'm going to create my second signal now. I'm going to let y of n be equal to, in this particular case, I'm going to let it be minus u of n minus 1. So it's going to be a shifted unit step, and it's also going to have that -1 weighting on it. We can certainly take the transform of this as well in simple ways. For right now, since we haven't done this one explicitly in the past, I'll go ahead and just compute it by direct definition. So I know y of z here is going to be a summation. Now this signal is non-zero only going from 1 to infinity. So the sum limits here are going to go from 1 to infinity. Over that region, the signal is -1, and then we have that z to the minus n factor out front. This is a geometric sum, right? So this geometric sum is going to have that -1 scale factor. The ratio here is z to the -1, right? So I'm going to have z to the -1, or 1 over z. So I'm going to have z to the -1 raised to the lower limit 1, minus that ratio again, z to the -1 raised to the infinity plus 1, if you want to call it that, all divided by 1 minus the ratio 1 minus z to the -1. That infinity term, we want this guy to converge. This thing will converge as long as norm z is greater than 1. So this second term in the numerator goes to 0 if norm z is greater than 1, which means we're outside of that root, which we see in the denominator. So the denominator here has a root at z equaling 1. We know roots can't be included in region of convergence. To get that convergent behavior, we do have to specify that part of the z-plane that it converges. We're almost done here, so I'm going to keep going a little bit. We have that yz then being equal to, and we have a minus, right? And then we're going to have a z to the -1, z to the -1, minus 0, nothing we have to worry about there. and then we're going to go ahead and have a 1 minus z to the minus 1 in the denominator. I want to get this in a little more familiar format, so I'm going to multiply top and bottom by z, and that's going to give me a minus. Z times z to the minus 1 is just a 1, and I have a 1 minus, oops, not quite 1. Got to multiply my z through there. I'm going to get a z minus a z times z minus 1. That's going to be my 1 down there. So I'm going to get a total transform here of minus 1 by z minus 1, and my region of convergence Ry is such that norm z is greater than 1. All right, so let's summarize these two transforms. I have x of n being equal to u of n, right? And it has a transform z by z minus 1, and its region of convergence Rx is such that norm z is greater than 1. We had another signal y of n, and that was equal to minus u of n minus 1, and we had its transform being minus, and I had a 1 by z minus 1, and its region of convergence, we called that Ry, was again the same thing, norm z greater than 1, something along those lines. So I've got my two signals and I know what their transforms are. Now we can go back to that linearity property. Let's take a linear combination, and the particular combination I want to look at is just the simple sum of x plus y. So I'm going to go ahead and add x and y, and I'm interested in what is going to be my transform on this, the z transform of this. The linearity property says I just take the transform for x, which is z by z minus 1, and I add to that, right, the transform for y, which was a minus 1 by z minus 1. This first one had a region of convergence norm z greater than 1. The second one also had a region of convergence norm z greater than 1. The intersection of both of those just gives me norm z greater than 1, something along those lines. Now we could sit there and say maybe that's it, maybe we're good to go, but this is one of those special cases where the at least condition comes into play. The at least really is just reflective that sometimes linear combinations cause a cancellation of a pole, and that cancellation of a pole can cause the region of convergence to expand. To see that, let's go ahead and take a look at the combination of my two transforms, x of z and y of z. If I do a little algebra on that, I know that I get a z minus 1 over a z minus 1, which is just equal to 1. There is no pole at 1 in this case, because the combination introduced a 0 at 1 that covered up or canceled that pole at 1. As a result, my region of convergence is no longer bounded by that pole at 1. It has free reign to go bigger than that. And so what we're going to find out in this particular case is that the region of convergence, there's no value of z here that it blows up. The region of convergence is all z. So we took the intersection of the two region of convergence, Rx and Ry. We got that norm z greater than 1, but because the pole was canceled through that linear combination, we saw that the region of convergence actually increased in size. It got bigger. So it was at least as big as norm z greater than 1, and in fact was a bit bigger. If I wanted to go just a tiny bit more on this particular example, something else I might notice here is that x of n plus y of n, if I just did the time domain expressions, that's u of n minus u of n minus 1, which happens to just be a delta function, delta n. So if we take a look at that signal, it's 0 everywhere, right? It's just a 1 at 0 and 0 following that. We'd already looked at the transform of that guy. The z transform of delta n, right, was equal to 1 for all z. We just had a different way of getting that result. We did it as a combination of x and y, and we found out that in this particular case, the region of convergence expanded. So we do have this linearity property of the z transform. That linearity property is exactly the same as the linearity property that we saw for the Laplace transform. Serves the same kind of purpose, functions in much the same way. The next property that we're going to talk about is related to a shift property. We're going to break this up into two different directions just because they behave kind of differently. So I'm going to start out by talking about a right shift property. So we're going to be talking about moving things to the right and seeing how that manifests in the transform domain. I would like to make a comment here. There's a bunch of notation that we see oftentimes with signals. So sometimes we'll see a signal like an x of n. Sometimes we might see a signal like x of n u of n. You could think of that as taking the causal part of x of n or making x of n causal, you might see stuff like x of n minus 1 u of n, and you might have things like, let's say, x of n minus 1 u of n minus 1. My comment here is that all of these guys, these are all different. They all mean something slightly different. Yes, they all involve x, but they involve x or utilize x in different ways. So every single one of these four that I've drawn out here, while they seem related to one another, they are all different. You should absolutely be comfortable with the differences between xn, xn un, xn minus 1 un, and xn minus 1 un minus 1. If those seem a little bit rusty to you, or that you aren't quite sure you understand the difference, I encourage you to go back into the book and read about it. They do a nice job of making sure that you have a handle on the difference between each one of those. So for me to get into this right shift property, I'm going to do a little if statement. I'd just like to start out with a beginning condition, and we're going to say something like this. Let's say if I have an xn u of n, and I go ahead and take its transform, and I let that transform be an x of z. So I'm going to call my causal signal here, xn un, having some transform x of z, and I'm going to allow for some parameter m being greater than 0. Then we can do something like this, that if I take x of n minus m u of n minus m, because m is greater than 0, this is just a right shift by m units, and I take the z transform of that guy, we're going to find out that that shift manifests itself as a z to the minus m term multiplying my original transform x of z. So some things to think about here, right? We had a signal x of n u of n. That was a time domain expression. We got a frequency domain expression, cap x of z. Whatever character there was in xn in the time domain, it's reflected in this transform domain signal x of z. When I look down here at this shifted version, x of n minus m times u of n minus m, that's just a simple shift, right? We take this first one and we shift to the right. We shift to the right by m, right? M is positive. So we're going to shift that guy by m units to the right. If we shift a signal to the right, it doesn't change the underlying character, right? The character of the signal is itself the same. And we see that in the transform domain, because the transform domain still has that x of z. That x of z tells us everything that there was about x of n u of n, right? It tells us all that that made up that time domain signal, just represented in the frequency domain. The only extra little piece is we get something out here, the z to the minus m, and we interpret that as telling us that the time domain signal was shifted by m units. If I wanted to prove this, we aren't going to prove every property, but we'll go ahead and prove this one because it's not so bad. It's a pretty reasonable one to prove. Let's just go ahead and do it by definition. I'm going to have here a summation. I'm going to let that sum go minus infinity to infinity. I'm taking the z transform. I'm going to take the z transform of that shifted signal. So I have x of n minus m, and I have u of n minus m. Those have to weight that exponential z to the minus n, and I need to be able to handle this guy, this particular sum. For me right now, I'm going to go ahead and do a change of variable. I'm going to let n prime equal n minus m. And if I solve that for n, if I solve that guy for n, I would find out that I would get n equal, just bring m to the either side, add m to each side, I'd get an n prime plus m. So I'm going to go ahead and make that substitution into the sum and see where I get. So I'm going to be now summing not on n, but I'm going to be summing on n prime, and we'll figure out the limits here in a second. We're going to have x of what? N minus m is just my n prime, so I'm going to get x of n prime. I'm going to get u of n prime, and I'm going to get z to the minus n, but n is just n prime plus n. So I'm going to get a minus n prime, and I would get a z to the minus m. I'm going to break that up as a product of two exponentials. We can do that since it was just a base raised to a sum. A base raised to a sum is just a product of two exponentials like that. What are the limits? Well, if n went from minus infinity, n prime is going to go minus infinity minus some finite number. Well, that stays at minus infinity. And if I look at the upper limit, I take n equals infinity and I subtract from it a finite number. It's still infinity. So the sum limits still say minus infinity to infinity. There is one term here that we should be able to do something with. There's the z to the minus m term, right? That is not a function of the sum variable n prime, and as a result can be brought outside of the sum. And so I know that this whole thing, right, just becomes, and I can write this out, z to the minus m, and then I've got everything left over. The things left over is just by definition the z transform of x and un, which we said was x of z, and now we finished the proof. So we know that the transform of the shifted function is just the original transform weighted by z to the minus m. A shift to the right, is just going to manifest itself. It's just going to show itself as that z to the minus m term. Powers of z, just give us an indication of shift. Actually, we could have guessed part of this based on some other material we saw in a previous lecture. Let me just do a very quick reminder of that. We had looked at a previous case where we looked at a delta function, a discrete, so this is a Kronecker delta function. So I'm doing this as a function of n. It has a height 1, and so this is my delta n, right? And we did in this particular case for this signal, we did a z transform on that. If I wanted to call this whole signal here x, right? Cap x was equal to 1, my cap x of z. That was a transform we dealt with before. We also looked at this idea of taking that delta function and shifting it over. So if I let it be 0 for a while and then I finally brought it back up, right? And I had that at some location m. This was a delta n minus m. When we z transformed that, what did we get? We got a z to the minus m, right? Well, that's z to the minus 1, or z to the minus m times 1. It's exactly following the shift property. So as I shift deltas to the right, I get negative powers of z. And you can guess what the left shift property is going to look like. We're going to get positive powers of z. But okay, so this thing should look pretty familiar. This one could have gotten not from the definition like we did previously, but just by using the shift property that we just derived. So we've got that basic shift. Let's talk about the shift in a little bit more specific case, considering really a unilateral transform. It turns out that the shift property is really important to understand from the unilateral transform property perspective, because it's going to allow us to solve difference equations with initial conditions, much like understanding the derivative property for Laplace transforms in the unilateral case allowed us to incorporate initial conditions. So let's go ahead and think about this unilateral case. So let's think more along the lines of the unilateral z transform, right? And this right shift property, So I could have in here a signal x of n, and because I'm going to do a unilateral z transform on it, right, that's going to be a summation going from 0 to infinity of my x of n z to the minus n. We've seen that before. The unilateral just has that lower limit of 0. Now, if I shift that signal by 1, so if I look at x of n minus 1, and then I want to take the unilateral transform, I can think about that or accomplish that regardless of the transform I want to take just by multiplying it by un. Un says make causal that signal that results after I've shifted it, something along those lines. So this is going to allow me now to again take this unilateral transform. It's still going to be a summation from 0 to infinity. And so I'm going to have my n equals 0 to infinity, x of n minus 1, my shifted signal, but I'm looking at it in the unilateral case, z to the minus n. And I would like to get a handle of what this guy's looking like. In this particular case, again, I'm going to go ahead and make that same sort of substitution that I did before. So I'm going to create a new variable n prime, and I'm going to call it n minus my shift. In this case, the shift is 1. I can also solve that for n, and n is equal to n prime plus 1, something along those lines. Go ahead and make those substitutions into this, and I'm going to get a summation. That summation is going to be on n prime. We'll talk about the limits here in a minute. But then I'm going to get what? X of n prime, and I'm going to get a z to the minus. Well, what is n? N is n prime plus 1. So I'm going to get a z to the minus n prime, and I'm going to get a z to the minus 1 in there. Now, when I think of the limits, my original limit n was 0. So when I find out what's the corresponding of n prime, 0 minus 1 is going to give me a lower limit of minus 1, not 0 now. The upper limit is going to be infinity minus 1. That's still infinity, so I still have an upper limit of infinity. So I have a sum now that is going on n prime, going from minus 1 to infinity of x of n prime z to the minus n prime z to the minus 1. Again, this z to the minus 1, right, is going to be something not a function of the sum variable. I'm not going to quite mess with that right now. Instead, what I'm going to focus on is the sum piece here. that sum piece has a lot of terms, right? There is an n prime equaling minus 1 term, there's a 0 term, there's a 1 term, and a 2 term, and it goes on out to infinity. I would like to group all of the 0 to infinity terms together, and then I'm going to leave all the stuff that corresponds to negative values of n prime and treat those guys separately. So let me break that big sum up into a little sum. So that sum going n prime minus 1 to infinity, I'm going to take the first term, n prime equaling minus 1, and I'm going to get an x of, well, n prime is minus 1, so I'm going to get an x of minus 1. I'm going to get a z to the minus of minus 1. That's a z to the 1 times z to the minus 1. So that's z to the 1 minus 1, or z to the 0. That's just 1. So that first term won't actually show a z in this case. It's just going to be little x of minus 1. And then I have everything else. Everything else is n prime going from 0 to infinity of x of n prime, right? Z to the minus n prime, and I still have that z to the minus 1. Okay, at this point now, I can take that guy and move it out, and everything else that was left over there was my original signals transform. So what do I get out of this? I get a little x of minus 1 plus z to the minus 1 x of z, something like that. So this is what? This is the unilateral transform, z unilateral, of a signal that's been shifted over by 1, something like that. And what we find out is that we get some familiar pieces in here, right? We know that that shift right shouldn't change the signal much, so we still have that x of z, and we have that z to the minus 1 term, which really interpreted just says, hey, shifted over by 1. But then we see this extra term. This extra term is that initial condition dependence. So what we find out here is that by taking the unilateral z transform of differences or delays, right, we start seeing these initial condition terms come up in the transform domain expressions. It's a way for us to incorporate initial conditions when we're trying to solve boundary value problems that involve difference equations. If you want to think about this in just a little different way, we can go back to the Laplace domain and think about the equivalent for a Laplace type operation. I'm going to go ahead and think then that if we took the Laplace transform of something like, let's say, x dot, take the Laplace transform of a first derivative, what did that go to? That went to an sx of s. So that was a bilateral Laplace transform. If we had a derivative in time, we got multiplication by s, right? And then the original transform. Think about what derivatives are like for a discrete time signal. We've seen this before. Derivatives can be approximated, or they are analogous to a difference. So that's like something like we had seen before when we did our first shift, right? We took our first shift over here. We said that when we shift a signal, we end up getting the original transform right back, and then we just get a power of z. It's a negative power of z, but a power of z. So a power of our frequency variable times our transform. Same sort of thing for derivatives in Laplace. I had a derivative in time, and I got a power of our frequency variable times our transform, something like that. Now, we also looked at the unilateral Laplace transform, and we also applied that to things like a first derivative. And what did we get? We still got that s, x of s, right? So we still got that idea that you had a signal differentiated. That's what the multiply by s means. But then we also got an extra term in there, minus x of 0, time domain initial condition. The unilateral transform that involved a derivative gave us the expected kind of transform part, which was the variable s times the transform, but then we got that dependence on the initial condition. So we use the unilateral transform, unilateral Laplace transform, to help us solve boundary value problems for differential equations. So those differential equations that had initial conditions, we're going to do the same thing up here for the reason of using the unilateral z transform. When we're trying to solve these difference equations, it's going to allow us to solve them and incorporate especially those initial conditions. So we're going to definitely see this come up in an analogous way to how you use the unilateral transform incorporated with derivatives. Now, we only did the first order delay there, so we probably should generalize this so that we can get higher order delays, handle higher order difference equations. So I'm going to do this one without proof, x of n minus m. So I'm going to just go ahead and delay that, or shift right by some amount m, and then we'll make it causal. That's corresponding to that unilateral transform, making it so that we're forcing it to go from 0 to infinity. So you can think of this as then we're going to do the unilateral z transform on that guy. We are going to get a z to the minus m x of z. That's the expected piece. You get that shift indication by the z to the minus m. You still have the x of z. What we have to do to this is we have to add some correction terms that depend on those initial conditions. And they look like this in the general case. We're going to get a z to the minus m, and we have a summation here. That summation is going to go 1 to m, and I'm going to have little x of minus n and a z to the n. And so what we find out is that this set of extra terms, right? There are m extra pieces, and what they involve are things like x of minus 1 and x of minus 2, going all the way out until we hit x of minus m. Those are the initial conditions for an nth order delay or an nth order system. So it's exactly like we'd expect. An nth order delay, which would result from an nth order difference equation, can support m initial conditions, and we see all m of those initial conditions explicitly get incorporated in our transform domain expression as long as we use the unilateral z transform. It all is exactly like what we saw with Laplace and doing derivatives. Derivatives are the operation for continuous time. Delays are the operation for discrete time. So we can also look and do this all in terms of a left shift as well. I'm again not going to do any proofs on this. We'll just write the result. Left shift, so moving things off to the left, is less common for us. Usually we're doing delay versions. That's connected to some of the causality when we actually do this as a system. But still, there are times that we do left shifts as well. So I'm going to write that out as an x of n plus some cap m u of n, something like that. And that would transform to not a negative power of z, but a positive power of z, weighting our x of z. And then we have these extra terms, minus z to the m. This is a summation n equals 0 to n minus 1. That's an m minus 1. And then I'm going to have my little x of n and a z to the minus n. So we get something that's a lot like those initial conditions. These extra terms in there, basically what they're doing, if you look at the terms in there, there's an x of 0 and there's an x of 1, and it goes all the way out to an x of m minus 1. And what we're doing is we're basically getting rid of the impact of those points as they related to my original transform. Let me just do a very quick picture of what this might look like. Suppose I had a signal, an original signal, x of n, that looks something like this. I had a value 1, and I had another value 1, and then maybe a minus 1 and a half, and a minus half, and another minus half, and it just is going to repeat those guys. And then I decided that I'm going to shift over by m equaling 2 to the left, something along those lines. So what would I get in that? If I shifted this guy over by the 2, I would get something like there would be this 1 and that 1, and then I would have that minus half plus half minus half plus half minus half plus half, something like that. This whole piece, right, when we transform it, that's the thing that gives us that x of z. Wow, that's not working so great. Let's get rid of this really bulky green and just make a finer green. So we know that that whole thing goes to an x of z, right? That whole shape, the two ones followed by these alternating halves, right, is what is x of z. Now, if I want to shift that left by 2, right, I should have a z2 x of z. That's like what we have right there, right now, right? Something along those lines. But when we do a unilateral transform, that's this u of n part that you could think about there, it is doing what? It's ignoring these two pieces. M equals 2, a shift by 2, means two guys get shifted out because it's a left shift, are getting shifted out of where the unilateral transform would look. So we need to get rid of whatever information or whatever contribution those 2 points had on my original x of z. Well, guess what? That's exactly what those terms do. So we have the z squared x of z, and then we're going to do this correction term up here that involves x of 0 and x of 1. Because what is x of 0 and x of 1? That's those two ones. They're no longer there. Their contribution is getting subtracted out. So we're going to have a minus, and we'd have here a z squared because our m was 2. Then we have a sum here going from 0 to 1. The first one is going to be little x of 0, right? And I'm going to have a z to the 0, so that's just going to be little x of 0. And then I'm going to add to that little x of 1, and it's going to have a z to the minus 1, something like that. So let's break that out and look at it. That's a minus z squared x of 0, and it's going to be a minus z, because z to the squared times z to the minus 1 is just z, and that's a little x of 1, something along those lines. So what does this tell us about? Well, we've seen this sort of thing before as well. Little x0 is just a value, right? Z squared is a delta function at minus 2. So there it is at minus 2. We have a delta function, and its height, right, is little x of 0. And we're just subtracting out, getting rid of that component from what had already had that piece, that x of z. And the same piece over here. Z is just going to give us a delta function at minus 1, and we had that term x of 1, and we're going to subtract off the content of that piece as well, because they are not included in that unilateral transform. Okay, so those were both cases of shift, both left and right, involving the unilateral transform. The right shift, we see it incorporating initial conditions. The left shift, we see it doing some corrections, getting rid of the terms that were getting shifted out of the window of the unilateral transform. The next property that we're going to look at, so I think we're on the third one right now. So this next property that we're going to look at is multiplication by an exponential. So this is multiplication by an exponential. This is a time domain of multiplication. Let's let that exponential have the form alpha to the n. So I'm looking at what happens when I take alpha to the n times a signal, known signal x of n. We know it's transform. That guy ends up having a transform that's going to be cap x, okay? And it's just that now instead of a function of z, it's going to be a function of z by alpha. There is a change in this particular case. If it was a bilateral transform, the associated region of convergence of this exponential scaled signal is going to be the region of convergence of x, also scaled by the size of that exponential base, alpha, so norm of alpha, something along those lines. If I wanted to get a handle on this and think about why this property might be true, we can quickly go through a proof here. I don't want to do too much on this because it does get a little bit tedious, but alpha to the n x of n, whoops, I need to have an x in here. So alpha to the n x of n, we're interested in what happens when I do the z transform on that guy. I'm going to have a summation by definition, n going from minus infinity to infinity. I have my alpha to the n in there. I have my x of n in there, and I have my z to the minus n in there. I'm going to go ahead and just combine my alpha to the n and my z to the minus n. So this is a direct, easy kind of combination. I still have a sum, n going from minus infinity to infinity. Alpha, z to the minus n is just 1 by z to the n. So I'm going to have alpha to the n over z to the n. I have two different bases, but the same exponent, so I can write that as an alpha by z to the n, and I'm multiplying that by x of n. I probably should have written that the other way, but what we recognize here is that that equation, this thing here, looks exactly like the z transform, not of the variable z, but of the variable alpha by z. And so what do we see this whole thing is? This is the z transform of x, but not of z, but of alpha by, not alpha by z, it is z by alpha, because it should be a minus 1. Let's go ahead and finish that. Let's do one more. We'll do one more on this, make that totally clear. Let's rewrite this one more step. So I can write this as a summation n equals minus infinity to infinity. I have my x of n, and I want something raised to the minus n. That's the form of a z transform. Well, to make alpha by z to the n into something to the minus n, I just need to reciprocate that interior piece. So z by alpha to the minus 1 will give me alpha by z, then raised to the n. So now we're there. This piece now, we recognize this whole thing, right, is just x of, it is my z transform, not of the variable z, but of the variable z by alpha, which is exactly what we wanted to show. We wanted to show that this scaling by an exponential just scaled our z variable, something along those lines. So that was our third property. We're going to go ahead and move into a fourth property. This fourth property is very, very similar to what we saw in Laplace. So this fourth property is going to be multiplying by the independent variable. In our case, it's the discrete independent variable n. So I'm going to multiply by n. If I look at that in equation form, that's n times x of n. So I'm multiplying my known signal x of n by the independent variable n. and I would like to know what its z transform looks like. Well, it turns out this one's going to have a form minus z ddz of x of z. And the region of convergence, the ROC, will remain Rx. It doesn't change the region of convergence in there. This one might seem a little bit weird. It might be a little bit hard to just get your head around and say, oh yeah, I just totally get that. That's totally obvious. It's probably not obvious to anybody who first looks at it. So we do want to spend a little time to try to get comfortable with that. Before I do that, though, I do want to think about what happens or what the similar one was for Laplace. We had Laplace doing what? We did something like t, and then we had an x of t. So we took a continuous time signal and we multiplied it by the independent variable t in that case, and we took the Laplace transform of that. And so if you go back into your sheets on that, I'm going to go ahead and grab my formula sheet on this. I'll just take 2 seconds on that. I'm going to open it up to the Laplace transform side in here, just to make sure I get it absolutely right. And I have in there a tx of t going to a minus dds of x of s, something along those lines. I'm not going to worry too much about what the region of convergence in there. It's also just whatever the original region of convergence is, but let's leave it at that. So multiplying by the independent variable times our signal, whether it's Laplace or z, does result in what? It does result in differentiation in our frequency variable, s or z, depending on whether you're continuous or discrete. Now there's this little extra z term out front for the discrete case. We probably need to figure out where that came from, and they both have a minus sign in there. So when you take a look at these things, whether it's a continuous time signal or a discrete time signal, you multiply by that independent variable, it does cause a differentiation type operation in the transform domain. So very, very similar. Let's go ahead and see or make sure that this property that we've written down is true. In this particular case, I think it's easier to work with the right-hand side over here, the minus z ddz of x of z, to try to show that this is indeed a correct property. So let's go ahead and start with that right-hand side. And I'm going to write out minus z, and I have my ddz, right, of x of z. But what is x of z? I know by definition, right, my x of z is just a summation on n, going minus infinity to infinity, x of n, and I have z to the minus n. Now, a derivative, right, a derivative of a sum can be just done as a sum of derivatives because differentiation is a linear operator. So I can go ahead and simplify this a bit. I still have the minus z out front, and I'm going to have my summation n equals minus infinity to infinity. And now I'm taking ddz of that x of n, z to the minus n. Well, x of n is just a constant with respect to z, so I can pull that also outside of the ddz operator, and I'm left with ddz, right, acting on z to the minus n, something along those lines. If I continue this a little bit, I'm going to get my minus z, and I'm going to have a summation here, n equals minus infinity to infinity. I have my x of n term, right? Now the derivative of a simple polynomial is simple, right? We get a minus n, and I'm going to get a z to the minus n minus 1, something along those lines. Now we're going to do a little bit of combination and simplification. If I take a look here, the minus sign there is going to cancel with the minus sign there. The z here, right, is going to cancel out that z to the minus 1 there, and I'm left with just a few extra terms out here. So I'm going to have a summation, n equals minus infinity to infinity. Now there's an n that was in there. There's an x of n, right, and I have a z to the minus n. Let me group that n x of n with some parentheses. So if I look at this right-hand expression that we just got to, what does this look like? It's a sum of some signal weighted by z to the minus n. That by definition is what? It's the z transform of n x of n. And that indeed, if I can get it all in one place, right, is what we were trying to prove. That the z transform of n x of n does go to minus z ddz of x of z. Proof is complete. It does seem to be right. So multiplication by an independent variable n or t ends up giving us differentiation, right, in the transform domain. So we have completed that particular one as well. The next property is also going to look familiar to stuff that you've seen before. This next property, I think we're on the fifth one now, is the convolution property. I know that convolution is everybody's favorite, so it's hard to believe that we'd want to do something other than do time domain convolution. But heck, if you got tired of it and didn't like it, the convolution property here will definitely help you out. What do we have? We have a time domain signal x of n, and we convolve it with another signal, call it y of n. Discrete time convolution, and we're looking at what happens under the z-transform operator. The guess here that you might have is probably the right one, that convolution becomes multiplication. It's one of the reasons we really like transform domain analysis. It doesn't matter if it's for continuous time stuff or discrete time stuff. Convolution in the time domain, discrete time or continuous time, becomes multiplication in the transform domain. Now, if we have a bilateral transform, we also have to handle the region of convergence. The region of convergence, much like one of the ones we saw before, is going to have this at least, because that multiplication could cause the cancellation of a pole. It is at least Rx intersect Ry. It could get bigger if one of your poles canceled. So convolution becomes multiplication. This one's not hard to prove. You just take the convolution sum here, you put it into the z-transform equation, and you go to town. It's a bunch of kind of tedious algebra. I'm not going to do it. It's exactly the same result as we saw for the Laplace transform. We don't really need to go through all the details on that. Details are online or also in the book. Sixth property that we could talk about. There is a time reversal property. Now, up to this point, many of the properties that we've talked about have both a unilateral and bilateral z-transform flavor. This particular one really is only for the bilateral case. And I don't think it's too hard to figure out why. If I time reverse a causal signal, it becomes anti-causal. And a unilateral transform of an anti-causal signal doesn't make any sense because unilateral expects causality. So time reverse just doesn't make sense for this idea of a time reversal property. What does the time reversal property say? It says if I time reverse a signal, I can get the transform with really essentially no work. All I have to do is reciprocate the frequency variable. So I'm going to take x of 1 over z, and the region of convergence as well becomes reciprocated from whatever the original region of convergence is. Let me just demonstrate this one through a very brief example. It won't be anything too terribly complicated, but it will show the basic idea of it. So I'm going to start out with a signal alpha to the n u of n. This is a signal we had looked at before when we first introduced the idea of a z-transform. We know its transform is z by z minus alpha because it's a right-sided signal. The region of convergence, right, the region of convergence that we have here is norm z greater than norm alpha, something like that. So I have a causal signal in this particular case. And what I would like to do is I would like to take this guy and time reverse it. So if I called this whole thing x of n, right, I'm going to be looking at here x of minus n, which is going to be alpha to the minus n u of minus n. And I want to know what its z transform is. According to the property, I just get it from x. But instead of using a variable z, I use 1 over z. So everywhere I see a z before, I put in, I put in a 1 over z. So I'm going to have a 1 over z and a 1 over z minus alpha. And I can do the same thing in the region of convergence. I'm going to have a norm 1 over z, right, greater than norm alpha. Let's do a little bit of simplification on this. I'm going to multiply this first one by z just to put it in a little more familiar form. That's going to give me 1 over 1 minus z times alpha. This other one I can write also in a little bit more normal form. I can write this for norm z, bring that to the other side, and then I'm going to bring the alpha back to the other side. This is going to be norm z less than 1 by norm alpha. So yeah, that region of convergence got reciprocated, right? Instead of being greater than norm alpha, it's now less than 1 over norm alpha. And we have our transform sitting over here, which is 1 over 1 by 1 minus z alpha, something like that. Does this make sense? Does this thing make some sense? I think one of the ways we can think a little bit about it is taking a look at that denominator. That denominator definitely has a root, right? So we know that there is a pole or a root in the denominator here when 1 minus z alpha equals 0. If I go ahead and solve that, that's z alpha equaling 0 or z equal, not 0. Got to get rid of that. let's go back just a second and fix that, equaling 1, that's going to tell me z equaling 1 by alpha. So the root here is no longer at alpha, it's at 1 over alpha, right? And what do we know? We know that wherever 1 by alpha is, let's let 1 by alpha be over there, a region of convergence can't include it, right? So we are going to have norm z, and it's going to have to be something that does not include that 1 by norm alpha. Now, because the signal is left-sided, right, we know that the region of convergence is going to point on the inside. So this is norm z less than 1 by norm alpha. So it's exactly as we would have expected based on this rational function for the transform. The fact that it has a root at 1 by alpha, this region of convergence definitely can't include that pole location, and we know it has to point inside. So to be a circle in its interior, a disk in the region of convergence, reflective of the fact that I have a left-sided signal. Okay, not too many properties left to go. In fact, there's really only one that I think we need to deal with at this point, and then we should be pretty close to done with this lecture. This 7th property then is going to be more diagnostic, much like it was for Laplace. This is for our initial, so we're going to have the initial value theorem, which we will call the IVT, and we will also look at the final value theorem. So we have initial and final value theorem, so final value theorem, FVT, something along those lines. Let's go ahead and look at the initial value theorem and see what it tells us. So the initial value theorem says this, that the initial value of my time domain signal, x of 0, is equal to, we can get it from a limiting process in the transform domain, so as z goes out to infinity, of x of z, something along those lines. This is very similar to what we saw for an initial value theorem for Laplace as well. I don't think this one, though, is as mysterious as Laplace. We can see this easily by just going ahead and doing some direct substitution. So this is a limit as z goes to infinity. What is x of z? Well, x of z is a summation, right? We're going to be going from 0 to infinity. This initial value and final value only really makes sense when we're talking an initial value at 0. So this is unilateral kind of stuff. So n equaling 0 to infinity, and I have an x of n z to the minus n, something like that. So that's just by definition. If I broke that out term by term, this is a limit as z goes off to infinity. What's the first term? It is x of 0 times z to the 0, that's just 1. The next one's x of 1 times z to the minus 1, that's 1 by z. The next one is x of 2 by z to the minus 2, that's 1 by z squared, and we keep adding in more. So look at what happens when z goes off to infinity. Well, this first one, nothing happens, right? It just stays there. There's no z to do anything. The next one, though, when z goes to infinity, because z's in the denominator, this whole thing goes to 0. And in fact, every other term after that also has a z in the denominator. And when z goes out to infinity, they go all to 0. There's only one piece that survives that progress of z going out to infinity, and it's x0. And so we get exactly as we would have expected, that x of 0 is equal to x of 0, right? That x of 0 can be gotten from our transform domain in the limit as z goes to infinity. So pretty easy to show the initial value theorem. The final value theorem has some conditions, much like some of the initial value, final value theorems of Laplace. It looks something like this. If we have z minus 1 as the condition, x of z has no poles outside the unit circle. Don't have to worry too much about this and where it came from at this point. Let's just take it as the condition necessary. We're not proving this final value theorem as such. Then what? Well, then the final value theorem, says the following. A limit, and let's just call it cap n going out to infinity of little x of cap n. So the final value that my time domain signal will get to, what does it asymptotically approach, can be gotten again through a limiting process in the transform domain, z going to something. We'll talk about that something here in a second. And it's going to be z minus 1 times x of z. What value of z am I going to? Well, it's going to be 1 here, something along those lines. For us to get sense of this, it might again look a little bit mysterious. I just want to get sense out of this by comparing it to the final value theorem of Laplace. The final value theorem in Laplace domain for a continuous time signal looks something like this. The limit is some parameter t went out to infinity of little x of t. So looking at the final time domain value, the asymptotic behavior of our time domain signal was a limit, what? As s went to 0 of s, x of s, something like that. So I just want to compare these guys and see if there's any similarity or not. We see that both are looking for what? The last value that we get out of these time domain functions. If we look at them, they both require something about the transform domain of our signal. They're both getting multiplied by something that is a function of the frequency variable, s or z. This first one is s. Where is that in the s plane? If I go ahead and I draw it in the s plane, right? If I think about just s, if you want to think about where there would be a root or what the corresponding root of that is, that's like at 0. So I'm looking at s going to 0, and we've got that s. That's like at the origin. Well, that's where DC is, right? If I do the same thing for the z plane up here, z minus 1, the root there is at z equaling 1. So that's this guy over there. And we see that here in the limit, z equaling 1. We're going towards 1. Well, what is 1? Well, that's just the DC point 2. So if you look at this final value theorem, they have a very similar kind of structure. Once you recognize that DC is in different places between the S-plane and the Z-plane. So I'm looking for the asymptotic or the kind of going out to infinity behavior of our time domain signal. We can get it in a limiting process by looking at our frequency variable going to where DC is, right? Multiplied by a polynomial root at that DC location times our transform. It has the same basic form. It's just modified a little bit for discrete time to reflect this different nature of the frequency plane Z and the fact that DC is at Z equaling 1, not at the origin, something along those lines. Well, I think that hits most of the properties that we really need to do. Good place to stop the lecture for right now. Next time, we're going to really spend a lot of time using these properties to do some calculations and hopefully get through things with more intuition and less effort. So more on that